Our control system is a tuned mass damper by Luke Meyer, Andrew Zorio, Bryce O'Donnell, Alejandro Rincon, and Jared Lebanon. Our dynamic system, a tuned mass damper, is a system that consists of large mass springs and dampers attached to a building to reduce its vibrations. For our example, we picked Taipei 101's TMD, which weighs 660 metric tons and is suspended by steel cables. Instead of springs, it uses viscous hydraulics to translate the momentum between the pendulum arm and the building.
The motion of a building with a tuned mass dampener, or a TMD, is modeled using two coupled equations. The first represents the building, where the mass, stiffness, and dampening interact with external forces like wind. The second equation describes the TMD itself, which moves relative to the building. By tuning the TMD's natural frequency to match the building's, the dampener encounters vibrations through opposing motion, while dampening ensures energy is dissipated efficiently. The tuned mass dampener system is continuous as it evolves over time in response to external forces, which is described by the differential equations previously explained. This can also be seen in this visual, where there is smooth and continuous movement from the buildings.
The inputs to a TMD system are external forces like Andrew was talking about, such as wind and earthquakes. The outputs are reduced building oscillations and stabilized motion. Sensors measure displacement, velocity, and acceleration of both the building and the TMD to ensure optimal performance. Here's a quick video to see the difference between a building with and without the TMDs and to see how big of a difference they make. On the left, there's no TMD stabilization, and you can see it takes much longer for those oscillations to come to a standstill.
There are a variety of TMD systems. In some applications, a passive system is used, where the TMD is tuned to match the natural frequency of the structure. As a result, there is no feedback loop or control law, as the system operates independently. Here we have a block diagram incorporating our PID controller. The input to the system is a force related to sensors to the PID controller. The controller, using the control equation shown, optimizes the TMD mass movement to counteract the force. Any disturbances are summed to produce a new signal. The actuator, in conjunction with the TMD, generates an output force to counteract the disturbances.
The global frame represents the building's absolute moment under forces like wind. This frame lets us measure the structure's overall response and the external forces acting on it. The relative frame focuses on the TMD's mass, which swings against the building's motion. By analyzing this frame, we can calculate how the dampener absorbs and dissipates energy. Together, these frames allow engineers to design TMDs that move out of phase with the building, creating an opposing force to minimize vibrations and ensure stability. The result, safer, more resilient skyscrapers in extreme conditions.
Thank you so much for watching. This is our list of our sources, and this is our final 320 project on TMD mass dampers. We hope you enjoyed.